Alright, so now today we're going to put the last piece of the puzzle together. And usually I do this earlier. Usually I do this right after work. But I knew people were going to be gone today, and so we did work and momentum, energy and momentum first. Now we're coming back to this notion of power. Now, what am I doing now from here to there? What did I just do? Power. Work. I did work, right? And that work caused the bowling ball to change potential energy, right? I increased its potential energy, right? Now, what's the difference between this and this?
The time.
Time.
So is power changing work over time?
Power is the rate of work. So, yes. So power is the rate of work over time. But because work is energy, it's also the rate of energy. Too easy. Now, what is the unit for power?
Watt. P.
Yes.
Watt.
Watt is the unit for power. And what does a watt equal?
Work per joule per second.
Good. Joule per second, because work and energy are both in joules. So the unit is watts, capital W, which is equal to a joule per second. And what you'll find we'll do on occasion is solve it for energy so that energy becomes power times time. But again, that's the same formula just for your energy. And this is, I should point out, what kind of P is that? It's capital P. Right. Little p is momentum. And are we done, bro? Okay, we're not done yet. Big hand. Okay. So big P is power. All right. So I could do something as easy as, well, you take the F3M. How much work is done when a 16 kilogram box is raised 8 meters? So we had a 16 kilogram block raised 8 meters. And we found the work was equal to the change in potential energy of that guy, which was mgh. 16 times 10 times 8. 1,280 joules. I could add a step to that problem and say how much power is required to lift that 16 kilogram blocks 8 meters in 6 seconds. Yeah, just do power equals work divided by time, or energy divided by time, and I'm getting 1280 divided by 6 is 21.7. Or 217, I mean? 213. 213 is a third watts.
So how does watt transfer to electricity?
We'll get to that when we get to, But it's the exact same thing. It's still the rate of power. I mean, it's the rate of energy. It's power.
Pretty much any equation where it has like a unit of time in there, you can just solve for energy first and then divide by time.
Oh.
If you were to give us the watts, we have the joules, we found out the joules, you could just do the opposite and find out.
Yes.
Joules and opposite.
Absolutely. All right. Now, there is one other form that I want you to learn for power. Power equals work divided by time, right? What does work equal? Yeah. F delta x cosine theta over time. What do you see?
Kinetic energy, right? Alive.
Yes. Velocity. So power equals Fv cosine theta as well. Possibly. Alright? So I could say something like, boy pulls his wagon as simple as this. The boy pulls his wagon at a constant speed of 2 meters per second by pulling at a 30-degree angle with a horizontal with a force of 10 newtons. How much power is required to keep the wagon moving 2 meters per second? And I know, again, power then equals...
That's just wrong.
equals... What is power equal?
Force velocity.
That's good. Force and velocity. Cosine of the angle between the force and the velocity vectors. Force is 10 newtons. Velocity is 2 meters per second. And angle between the force and the velocity vectors is 30 degrees. So if I'm in degree mode, and I do cos theta, I get, what's that, 0.88-ish? Or what's 0.87? What is cosine of theta? Cosine 30. Yeah, 17 sounds right. It's like
17.30.
watt. Watt unit.
Watt.
Yes.
Yeah, many other degrees.
Since I gave you the angle in degrees, you should be in degree mode.
But I got 41 something in cosine. 12 by 10 is by 2.
Alright.
You were ready to go to change your degree.
Probably.
do, or no, better yet, how much work do frictional forces do on the wagon in 8 seconds?
How do you figure that out?
Yes. How much work do frictional forces do in 8 seconds? And when I say frictional forces, I mean all of the drag forces that are opposing it. Friction, rolling friction, air resistance, all resistive forces. Okay, how much work do opposing forces do? Or resistive forces? In 8 seconds. Do we know how to do anything? What could we do?
Whoa.
Okay?
But you just switch it.
E equals W over T.
So it's work.
Work equals power times time.
Because it's moving in constant velocity.
And that's the work that
The boys.
the boy does on the wagon, right?
But because it's moving in constant velocity, there's no acceleration.
Exactly. But since it's moving at constant velocity, there's no acceleration, there's no change in energy, so the net work on the wagon has to be 0. So if the boy is doing, what's 136? If the boy is doing 136 joules of work, the opposing forces are doing negative 136 joules. And since I didn't ask, I just said how much, it's just a quantity, so it's just 136 joules. Does that make sense? If the wagon's not speeding up or slowing down or moving up or down an incline, how much is its energy changing? It's not. So there's no net work on it. So all the work he's doing is being canceled by